In this video, we're going to be covering gradients, directional derivatives, vector fields, differentials, the total differential. Let's get into it. First of all, we're going to be talking about a vector field. So what is a vector field? It's just some function that takes in this case, it's xy coordinate, so you can think about as a point on this xy axis. And the output of this function is some vector. So for every point in space, you're assigning a vector at that specific coordinate. All right? That's just a vector field. Every point has a vector associated with it. And we can describe this as f of x comma y is equal to p of x comma y comma q of x comma y. This function p determines the output for the x component of the vector. So the x component of the vector. Well, this function q determines the component for the y direction. All right, so this is the vector component in the y direction. And it's going to be very useful if I give you an example. So what do I mean by this p of x comma y, this q of x comma y? Let me show you. If I have a vector field f of x comma y is equal to xy comma y plus x, right? Let's say if this was my vector field. So how would this look like? Well, let's try out plotting some points. When I'm at the coordinate 0, 0, notice how that's at the coordinate 0, 0. And notice how when x is 0 and y is 0, this whole term is 0. So the x component of my vector is 0. And when y is 0 and x is 0, the y component is also 0. So at 0, 0, the origin, we have the 0 vector. Now let's consider the coordinate 1, 0. So when x is equal to 1 and y is equal to 0, 1 times 0 is 0. So the x component of this vector is 0. And y in this case is 0. And this is going to be 0 plus 1, right? So that's just going to be equal to 1, meaning that the y component of my vector is equal to 1. So it's going to go up 1 unit. Right? So you're just assigning every point a vector associated with it. And it turns out that if I actually graph all of this, let's consider why some of these arrows make sense. Think about what happens for p of x comma y. This is the function that determines the x component of my vector. So notice how when x is negative and y is positive, notice how a negative times a positive number yields a negative result. So as a result, all of the vectors here where y is positive and x is negative, it's going to have the x component that's negative, meaning that the vector is essentially going to point to the left, right? You see how the arrows, all these arrows, they have an x component that's pointing towards the left. And on the other hand, notice how on the other side, when x is positive and y is positive, you have arrows that are pointing towards the right. Because positive times positive gives you another positive number, so the x component there is going to be positive, points towards the right. And likewise, when both x and y are negative, it points to the right, because negative times negative gives you a positive x displacement for the x component. Okay? And the color of these vectors actually determines its magnitude. So that's just to avoid clutter on the screen. And the further out you go, you can think about it as the xy values are going to get larger and larger in magnitude. And as a result, you're going to be multiplying bigger numbers. The x component is going to get way bigger. And that's going to be represented by these other colors, these green and blue colors. This is where multivariable calculus starts to shine. I'll admit, the first couple of videos where you learn about dot products, cross products, those are the start of linear algebra. You're building your fundamentals. But now I feel like starting from gradients and multivariable functions, this is where multivariable calculus really does shine. And you're really able to use a lot of what you learned for real-world applications. All right. So the first thing we're going to talk about is the gradient. The gradient is a vector field. And it's written as this del symbol. So there's a del symbol, which is an upside down triangle. You might remember delta, right? Like delta x, delta y. The del symbol is just the upside down version of that. And this is going to be a vector field composed of the partial derivatives of the function with respect to the output f. All right, so you have your original function, which just, right, x, y, and z axis, your original function. Oops. Okay. Your original function can be looking something like this, right? This is f of x comma y, kind of like a sheet. And the gradient of this, the gradient of f, is the partial derivative with respect to x, and then the partial derivative with respect to y. And if there was f of x comma y comma z, then there would be a partial derivative of f with respect to z. All right. So that's just the definition of it. But we're going to make some nice observations about the gradient and some of its properties. And then maybe a little later in the video, we're actually going to see why those properties are true. And before we move on to the simulation and this gets really visual, let's just review one thing. Contour plots. Remember, contour plots, let's just create a contour plot. Contour plots define when the value of a function is a specific value. All right, specifically, most of the time you deal with integer values, and this is used for elevations, mountains, stuff like that. And if you have a function, let's say it looks something like this. That's our function. Well, one question to ask ourselves is, when is the height of this function 2? And in the set of all points on this function where the height of it is 2, that's going to be represented in your contour plot. So this isn't a gradient visualizer, but it's a contour plot visualizer. So if I set, let's say z is equal to 1, notice how the set of all points where our function is actually equal to 1, right, actually has the height of 1, well, it's going to be like a circle surrounding this parabola cup-like looking thing. So notice how if you were to project that to 2 dimensions, it would look like a circle, right? Circle centered at the origin. Right? If I wanted to find out all the possible points where my z value was equal to 2, well, then it would form a bigger circle centered at the origin. So therefore, that explains why we have bigger circles as we move outwards. As we move outwards, we're going to get larger and larger heights, right? Our height is going to increase. But so is this, I guess, the radius of our circle, right? As we go up and up and up, the radius of our circle also increases. So the circles will get bigger as the height gets bigger, right? Because the set of all points that actually meets that height criteria keeps increasing. All right, so when z is equal to 3, or when z is equal to 5, let's just say, right, it's going to form these circles. And that can be projected onto a contour plot, which helps you visualize everything. All right, now that we're done with Desmos visualization, let's get to the gradient visualization. So what do you notice about this? So let's see what's happening here, right? So we have our point, right? This is our point on the graph. And the plane in white, that's the tangent plane. So we're going to be talking about that as well, right? If I were to have a point on the graph, well, notice how there's going to be like a tangent line in the x direction and then a tangent line in the y direction, right? Because we're dealing with multivariable functions, there's going to be 2 tangent lines mainly, right? So in single variable calculus, you have a tangent line to a graph, but in multivariable functions, there can be multiple tangent lines. Tangent line due to partial derivative of x, and you can have a tangent line due to the partial derivative of y, right? And so 2 lines, if you remember back to geometry, that's able to form a plane. And we'll actually see how to calculate the tangent plane given a graph and a point. All right, so given the function and the point, calculate the tangent plane. That's a little bit for later. What do you notice about this graph? And what do you notice about this one? Well, these lines represent the level curves for our function, right? They represent the set of all points that where our height of the function is equal to some value, right? That just comes straight from contour plots. These are called level curves, by the way. All right. Now notice how the gradient vector, which is seen in green, so this is the gradient vector right over here, vector A, or I guess stems from the point A. Notice how it's always perpendicular to the level curves. All right. So let's actually write this down. So the gradient, or del f, that's going to be perpendicular to the level curve. So that's basically when z is equal to some value, let's say 1, right? Then you can define that in the coordinate plane, and there's your level curve. Let's take another observation at the gradient. Notice how the gradient's always pointing outwards. This is really interesting. But it looks like it's always pointing towards where the function is always getting increasing. So that was just, my words just got messed up there. All right. The gradient always points towards the direction of steepest ascent. It points towards where the function increases the fastest, right? You see how when the gradient is at this point right over here, notice how taking a step in this direction increases, right? Taking a step in the direction of the gradient, that increases the function the fastest. I can do another example. Let's say if this was x squared minus y squared. I know that's a mouthful to look at, but notice how when my gradient, or when my point is here, notice how the gradient points outwards, because it points towards the direction of steepest ascent, which in this case, it's going this way, right? So the gradient points the same direction, right? It points to the left in this case, right? In order to make my point higher, my point has to move in this direction, so the gradient points in that direction. So I can say that the gradient, that's somehow linked to the direction of steepest ascent. It points to the direction where the function increases the fastest. Now for the level curves, this is actually pretty easy to justify if you think about things conceptually. So think about it, right? We're on this level curve here, and we want to go to the direction where our function increases the fastest, right? After all, that's part of a property of the gradient, right? It tells you where the function increases the fastest. Well, which direction do I have to go for my function to increase the fastest? Should I go 1 unit this way, 1 unit perpendicular, or 1 unit this way? Well, notice how moving perpendicular always makes you increase the fastest, right? If I'm on this level curve, right, moving this way doesn't help much, right? Given like a fixed step size, imagine if you can only step 1 unit, right? If I can only step 1 unit, then this ain't getting me anywhere. But if I step perpendicular, that's getting me somewhere. If I step just slightly non-perpendicular, that doesn't get me as far, right? So you might have remembered this from geometry, but if you have a line and a point, the shortest distance from this line to the point is always the perpendicular distance. All right, because any other distance that you travel, any other path that you take, it becomes the hypotenuse of a right triangle. And the hypotenuse is always the longest side, so that's the longest route. The perpendicular distance is the shortest route. Okay? And we can actually do a little proof to explain why is the gradient perpendicular to the level curve. Why is that? Let's say that we focus on one of these level curves. All right, so recall that this level curve is essentially when our function f of x comma y, that's going to be equal to some constant, which I'll call c, right? That's when the function is equal to some constant. Now, what if I had a function representing the path of a particle along this level curve? So I only want to represent the path of a particle on the level curve. And it turns out that I can do something that we've done in previous videos. We can parameterize this, right? I can say that x is equal to some function of time, x of t. And then the y-coordinate is also expressed as a function of time, right? The y-coordinate can also be expressed as a function of time, and together they create our position vector, r of t, my vectored valued function. All right. If I substitute in x of t and y of t into my original equation, I just get that f of r of t, so do this in red, f of r of t is equal to some constant, right? These just represent the position of x of t and y of t, just represent the path of a particle along one of these level curves. But when we actually plug in the coordinate, the x and y coordinate into our function, we still get that same constant, right? It's still equal to that constant. So I just made this substitution here. What if we differentiate both sides? Let's differentiate both sides with respect to t. Well, so this is going to be the derivative of f of r of t with respect to t, and the derivative of this constant here is just going to be 0. So f, that's basically z, right? And r of t, well, that's just the inside function. So when I take the derivative of all of this right over here, what I'm really trying to find out is what is the rate of change of our function f with respect to time, right? What is df dt, right? Well, the rate of change of our function is going to depend on two factors in this case. All right, it's going to depend on two factors. If I consider a random curve, any surface, right? If I move a tiny bit in the x direction, that contributes to a change in the function height. But if I move a tiny change in the y direction, that also contributes to a change in the function height. So my differential, or in this case, this derivative, it has to consider how am I changing in the x direction and how am I changing in the y direction as well, because both directions now, right? Because remember, we're dealing with multivariable calculus. So instead of x variable changing the y variable, you have the x variable changing the z variable and the y variable changing the z variable. So it's a twofold impact, right? So I can say that the derivative of f with respect to time, that's going to be, well, how does f change, right? We want to consider how does f change with respect to x. And then we multiply that by how does x change with respect to time, right? Because a tiny change in time causes a tiny change in x, right? Because a tiny change in time causes a tiny change in x. And a tiny change in x causes a tiny change in the output of our function f. All right? So I know this seems very, very complicated. So sometimes it might be helpful to use a little graph thingy or like a little branch, right? The time variable affects both our x and our y inputs to this function. And then a change in the x and y inputs, they both affect the final output, which is f. So this little tree diagram is very, very useful for determining how variables rely on each other, right? Changing one variable, how does that contribute to the overall change? But not only does changing time affect my x variable, remember, this is a vectored valued function, right? My y variable is also going to be changed as well. So this is going to be how does f change with respect to y multiplied by how does y change with respect to time. Because changing time affects both my x and my y, and then changing x and y, they both affect f, my function f. And adding those little changes together gives me my overall change, df dt. Now, actually, these should be partial derivatives. So df with respect to x and then df with respect to y, because this is dealing with multivariable functions. So this is a little bit more accurate. But this is in essence the multivariable chain rule. You really do get to see how multivariable calculus shines, because no matter how complicated this graph is, right, if t depends on a variable u, this u depends on a variable v, you can always traverse this graph using the multivariable chain rule to determine how does one variable indirectly link to another variable, right? How does t indirectly link to f, right? Okay, we're actually going to see an application of how this can be useful, all right? But that's after this proof, which is going to end surprisingly shortly. Because notice how you have these components multiplied by these components. And we can express this as a dot product, right? So the dot product between a vector containing the partial derivatives, so you can think about as df dx, and then df dy. Imagine if that was one vector, and I took dot product of that with dx dt and dy dt. Well, that would give me this result that I have here, right? Now that would be equal to df dt, right? I can just express it as a dot product between two vectors. And what is this? What is this? This is just the gradient, right? This is just the gradient of f. And what is this? Well, dx dt and dy dt, that's just the derivative of the x component with respect to time, x prime of t. The derivative of y with respect to time, that's y prime of t. That's just the velocity vector. I'm just going to call it r prime of t. So essentially, when we take the derivative of f of r of t, right, which is the same thing as df dt, what we're really saying is that this is just going to be the dot product between the gradient vector and r prime of t. And we know that this overall change is going to be equal to 0 because we're staying on a level curve. Well, what do you notice? When the dot product of two vectors is equal to 0, that means that these two vectors are going to be perpendicular to each other. So imagine if I'm traveling on the curve, right? This is going to be my velocity vector, r prime of t, at that specific time moment. But this represents a velocity vector. This is saying that my velocity vector is going to be perpendicular to the gradient vector, right? That means this gradient vector has to be perpendicular to this level curve, right? So this would be the direction of del f. And same thing here, right? Imagine if I was traveling on the outermost curve, or the outermost circle, right? Let's say that this is going to be my velocity vector. Well, then my gradient vector, because it's perpendicular to it, it has to point perpendicular to my level curve. And so we just proved that the gradient is perpendicular to the level curve, all right? So that's the first property that we have down. And before we get to the proof of the second property, which says that the gradient is the direction of steepest ascent, I'm going to show you how this is very useful, all right? How the multivariable chain rule of expressing df dt, how that's useful. So let's say that we have this multivariable function f of x comma y. Let's say that's equal to x squared times y plus 3x. And let's say that this function is parameterized given x is equal to t squared and y is equal to t squared. And our goal is to find out df dt. All right, how does f change with respect to time? Well, the first method of doing it is just plugging everything in, right? Because if I plug, right, this is essentially x of t, right? Recall that this is how t relates to x. So this is essentially x of t, and this is essentially just y of t at the end of the day. But nevertheless, we're able to plug in x in for our x variable here, our y into our y variable here. So essentially, we can rewrite f of x comma y as just f of some function of time, right? So f of, more specifically, it's f of r of t, like what I've written before. But to simplify things, let's just call this f of t. Because we know that x is equal to t squared, so x squared is t to the fourth multiplied by y, right? So x squared multiplied by y, well, we know that y is t to the third. So t to the fourth times t to the third is t to the seventh. And then plus 3 times x, well, that's just 3t squared. So if I take the derivative with respect to time, right? So if I take the derivative with respect to time, I get that df dt is going to be equal to 7t to the 6 plus 6t. All right. So, of course, we're able to evaluate this at some point, right? If we want df dt evaluated at some time value, we're able to do that. But here's just the solution to it, all right? At any time period. Well, we can find df dt this other way, right? Let's find it the other way. So hopefully y'all know how to do partial derivatives by now. But df dx, well, the derivative of f with respect to x, you treat y as a constant. So this is just 2xy plus 3. And all of this is multiplied by dx dt. So the derivative of x with respect to time is going to be 2t. Right? Because imagine differentiating both sides with respect to time. You get dx dt is equal to 2t. Plus df dy. So you treat you treat x as a constant now because you're letting y vary and you're seeing how the function changes with respect to only y. So x is treated like a constant, so this is just going to be x squared multiplied by dy dt. Well, what is dy dt? So you differentiate both sides of this with respect to time. So this is just going to be dy dt is equal to 3t squared. Okay. I want to find out how t changes and how that affects f. And I know that x is equal to t squared and y is equal to t to the third power. Let's just substitute these values in for this. So I'm just going to get 2 multiplied by x times y. So x times y, that's just t to the 5th power plus 3 multiplied by 2t plus x squared, that's just t to the 4th power times 3t squared. So if we multiply everything out, we're going to get, what is this? This is just 4t to the 5th power, 4t to the 6th power plus 6t plus, and then this is going to be a 3t to the 6th power. So we end up with 7t to the 6th power plus 6t. And notice how that's the exact same answer as I did with just direct substitution. And you might be wondering, whoa, this is way more work than what we did earlier. And you could be right to the extent, right? That is right to the extent, but sometimes the substitutions can be really messy. I'm just going to make up a random example. Like imagine instead of x equals t squared, imagine if x was like e to the t squared minus sine of t. Imagine how terrifying it would be, and imagine if it was like the same scenario with y. Imagine how terrifying it would be to substitute everything in first and then like try and differentiate that. That would be an absolute nightmare. And you saw how when I differentiated x with respect to time, that was really easy, right? It was just like one-step process. And y with respect to t, that's also like a one-step process. So when the direct relationships between y and t are easier to differentiate than direct substitution into the entire thing, then the second method is often better. All right, it's often faster. But for simple ones, direct substitution is often faster. And I provided a simple example just to show you that these are equal to each other. But I'm just saying that for more complicated ones, you would want to use the second method. All right. So either direct substitution or the multivariable chain rule. In addition, we can also see the differential. All right. So you might recall that dy is going to be equal to dy dx multiplied by dx. And this comes from the fact that delta y is equal to delta y over delta x multiplied by delta x. This is perfectly valid because the delta x's cancel out, so delta y is equal to delta y. And then as you take a limit as delta x approaches 0, you get this differential up here, right? It's basically saying that if I take a tiny change in the x direction and I multiply it by the slope, dy dx, I get my tiny change in the y direction, right? That's how that works. While in 3 dimensions, a tiny change in z, just like the multivariable chain rule, it's caused by a tiny change in x multiplied by dx, tiny. If I want to find out df, so the differential, right, that's going to be equal to, well, how does the function change in the x direction, right? The slope in the x direction multiplied by that tiny change in x. And this is going to be added to, how does this function change in the y direction multiplied by that tiny change in y. All right. So when you're dealing with differentials in 3 dimensions, and I'm going to be repeating the same idea over and over again, right? You're going to be dealing with more components. So a tiny change in f is going to be caused by a tiny change in x and a tiny change in y as well, multiplied by how far you actually move in that direction. And if you want like an informal kind of thing to help you memorize this is just a chain rule, but if you multiply everything by dt, these dt's cancel out, and you're just left with the differential. So even though it's not really a fraction, dy dx can be treated as a fraction because of differential. All right. But promise that you never use the fraction to justify the proof. All right, that's a little too much. Now we're going to get into why the gradient is the direction of steepest ascent. All right. Now let's think about this conceptually first before we get into the mathematical directional derivative nitty-gritty of this. So the gradient points towards the direction of steepest ascent, and the fact that makes this really nice is the fact that this is a vector field. So I actually want to clear up this before we get into more stuff. So vector valued functions and vector fields, they're closely related, but they're not exactly the same thing. So the analogy for a vector valued function is that it's able to trace out the path of a particle. So you can imagine that, like if this was like the origin or your starting point, right? At some specific time period, let's say this is t sub 0, this is t sub 1, you're going to have a vector associated with different time steps. But a vector field, on the other hand, that assigns a vector to every point in space. So all vector fields are vector valued functions, but not all vector valued functions are vector fields. So it goes this way, but it can't go that way, which I'll put in red. It does not go this way. Okay? That's like a slight nuance that I keep saying vector a lot, so I might get confused on that, but I promise that hopefully this will break down nicely. Anyways, the fact that this is a vector field, it makes things really, really nice. Let's say that df dx, partial with respect to x, and let's say that the partial with respect to y is 2y. And you can also see that when I evaluate the gradient at the coordinate 1, 1, well, we're going to have just a vector that's pointing to the left and pointing up, right? Because this is just going to become 2 and 2. That's our vector at the coordinate 1, 1. So this is what it looks like. Now, why does this make sense? Well, let's think about df dx. So we see how df dx in this case, that's equal to 2. Negative 2, sorry. What does this mean? This means that if I decrease x by a little bit, my value of the function increases. All right, that's what this negative sign, that is the significance of a negative sign. When you have a negative sign inside your partial derivative, that tells you that at this partial derivative evaluated at this point, if I decrease my variable a little bit, then my function is going to increase. And if you take a look at the behavior of y is equal to negative 2x, well, y is equal to negative 2x, that's just a line with slope of negative 2. And notice how if my x decreases, meaning that we move to the left, right, as our x value decreases, our y value increases. So we're going in the negative direction. We're going in the opposite direction of where this line is pointing towards. All right. So if our slope is negative, we go in the opposite direction. But if our slope is positive, like this 2y right over here, so we see how df with respect to y, partial with respect to y is equal to positive 2. When df dy, when that's positive, right, it's positive 2, what that's really saying is that when y increases, df increases as well. All right, that's the significance of the positive sign. And what that means is that if we look at this function right over here, 2y, well, that looks like a straight line that's going up. And so if I increase my y value by a little bit, well, then the overall function is going to increase. So in this case, This would be a function of y and z, or y and f. And then as y increases, our function f is also going to increase because it's positive 2, right? The slope is positive 2 between those two variables. So the main point I'm trying to make here is that at every single point, you can imagine doing this for every single point. When the slope is positive, then if we increase the y value, our function increases. When the slope is negative, all the gradient does is it just goes in the opposite direction. That means that when my x value decreases, my function is still going to increase. It's going to point towards the direction of steepest ascent, right? It always increases this way because this is a vector valued function and because of this geometric meaning of the graphs, all right? Now, in order to determine why the gradient is the steepest ascent, we have to get into something called directional derivatives. Directional derivatives. And directional derivatives are a pretty simple concept. Imagine if you have a function, so I'm just drawing this cone function that we saw before. And this is, let's say this is going to be the x-axis, this is the y-axis, and this is the z-axis, right? And let's say if we pick a point on this. So this point, right over here. Well, we saw how if we move in the x direction, right, just a tiny change in the x direction, and we see how that affects the height of the function, well, that's just going to be partial f with respect to x. If we move slightly in the y direction, right, a little dy, and we see how that affects the height of the function, right? This is a little df. Well, the ratio of those changes tells me the slope in the y direction, or dy over, or sorry, the derivative of the height of my function with respect to the y value, in this case, moving in the y direction. But if I'm at a point, I can move in any direction. I can move here. I can move in directions that are not just the x and the y axis direction. I can move all sorts of places. I can move in a combination of an x and a y direction. All right. And it turns out that at a single point, I mean, there can be infinitely many directions that you can move in, infinitely many vectors. And the directional derivative basically tells you, if I move in a direction of a vector at a specific point, how is that going to change the height of my function, right? What is the derivative of f with respect to the vector direction that I move in, right? So if this is a tiny vector v, how does the function f change in height with respect to the movement in v direction? Another way that you might see this written, another very common way, is this, you have this del operator. You have our function f, and it's in the direction of some vector. And the convention is that you got to normalize this vector. So this vector has to be unit length, which is very important. All right. Well, that's just the concept of directional derivatives. If you understand that directional derivatives basically encapsulates how does our function change when we move in any direction, any vector pointing to somewhere. That's directional derivative. So let's actually write this down. So imagine if my vector v has the coordinates a comma b. All right. What this is really saying, what df dv is really saying, or the directional derivative in the direction of v is saying, is that this is going to be very similar to the derivatives that you've seen before, but this is going to be f of x plus ah comma y plus bh minus f of x comma y divided by h. So if I move a little bit in the x direction, right, from the x component, right, so given this x component here, I'm going to move a little bit in the x direction, a times h here. I'm going to also move a little bit in the y direction given my y component, b. And as I take the limit, as those little direction changes go to 0, well, how does that affect the change in f, right? How does that affect the height of my function, df? And so the ratio of those changes, right, df dv, that's going to give us the directional derivative. Okay? So you see that these definition of derivatives, they're very, very similar. All right? It's not much different from what you see in regular old single variable calculus. Now computing the the directional derivative is actually pretty simple. I don't know why I said divergence there. But it's going to be the dot product between the gradient of f and the vector. All right. And that's assuming that the vector is already normalized, so it's already unit length. So now we're going to move on to our final topic, which is how do I find out this tangent plane? Right? So at any given point, there's going to be a plane that's tangent to the point, right? And how do we find that out? Because I know how to find the tangent line with respect to the x-axis. That's just the partial with respect to x. But you also have the partial with respect to y. And somehow we get this nice plane that also forms the tangent plane. So given these two tangent lines, how do I find out the tangent plane? That is the question. Let me answer that right now. There's actually two perspectives on how to get the tangent line, and we're going to be looking at both of them. So let's move on to the first method. So the first method is using the cross product and the point normal equation for a plane. So if I take a look at this simulation, thank you so much for GeoGebra for creating these simulations. It has been very, very amazing. Let's say that this is my surface, right? And I'm at this specific point A. Now at this point A, there's going to be the partial derivative with respect to A, right? So the partial derivative evaluated at that point, right? That's the partial derivative evaluated at that point. It tells you the slope, right? Moving along the x direction. And you also have the slope moving along the y direction, right? So if I move more to the right in this case of my diagram, I don't know why I do this, but if I move more to the right, you see that my slope is decreasing, right? The slope is getting more and more negative as I move to the right, right? Because it's decreasing with respect to y. And so together, both these lines, they form a tangent plane. And you can see that no matter where I go, right, my partial derivatives, they form a tangent plane. So you notice how in this diagram, there's going to be two tangent lines, right? The first tangent line is with respect to x, and the second tangent line is with respect to y. And we know how to find these tangent lines. We use linear approximation. So if you remember from single variable calculus, we can say that delta y, a tiny change in y, is caused by the slope in the x direction multiplied by that tiny change in x, right? And recall that this is going to be the differential for single variable calculus. And you might have seen it written like, dy is equal to f prime of x multiplied by dx, right? But if we're doing linear approximation, well, instead of dealing with a tiny change in x, it's going to be like an actual finite number. Now, we can get the tangent lines at that specific point A, right? No matter which point we are on, we can always calculate these two tangent lines. And how can we do it? We use linear approximation, right? So from single variable calculus, right, if I have this function here, I'll just draw like a better version of that. If I have a function here and I'm looking at some point A, let's just say this is f of A, right, some random point. Well, the thing is that if I zoom in to my function and close enough, it starts looking more and more like a straight line that I can use to approximate the value near that point, right? So lines can be used to approximate values near the point that you're focusing on, right? And recall that the linear approximation formula, well, let's say that this point right over here is at the coordinates x of 0, comma y of 0. And let's say that the slope at that specific point is f prime of x of 0. Well, I'm given a point, and I'm given a point on a line, and I'm given the slope of the line. So to find out the equation of the line, you use point slope form, right? That's how this is derived from. So this is y minus y0 is equal to our slope, m, or in this case f prime of x0, multiplied by x minus x0. And then so to find the equation of the tangent line, just move this y0 to the other side, and you get your answer. So if I'm trying to find out the equation of a line with respect to y at this given point x0, y0, z0, well, that's just going to be equal to the change in the z value. That's going to be equal to our derivative with respect to y. So let's say that I'm trying to find out the equation of my two tangent lines. Well, the tangent line with respect to x at this point, x0, y0, z0, that's going to be z minus z0, right, the change in z. That's going to be equal to the derivative with respect to x, evaluated at that specific x0, y0 coordinate. Right, that's just representing the slope of our line with respect to x. And then that's going to be multiplied by a tiny change in x. In this case, I'll just write it as x minus x0. And then the tangent line with respect to y, it's literally going to be the exact same thing, except we're looking at everything with respect to y in this case. So this is going to be the derivative of the partial derivative with respect to y. And then instead of x minus x0, this is going to be this is going to be y minus y0. So note that for the equation of a plane, we have two tangent lines, but really the only thing that we need is two tangent vectors, right? Because then we can use those tangent vectors to compute the cross product. So these tangent vectors, notice how they're parallel to my tangent lines, but at the end of the day, it doesn't really matter because the cross product determines orientation. So if these two things are parallel to their respective lines, then the resulting vector will still be a normal vector. They're still on the plane, right? So imagine, let's write out the tangent line, the tangent vector for our first equation here. So imagine if I change my x value by a little bit while keeping my y value constant. Well, then my corresponding function change is going to be f sub x, the partial with respect to x, multiplied by delta x. This just comes straight from this equation, right? And likewise, if I keep x constant, but I change y by a little bit, well, then my corresponding change in z value is going to be partial with respect to y multiplied by delta y. Now, this delta x and this delta y, the only thing that they really do is they scale up our tangent vectors, right? If delta x was some really big number, then the corresponding output is going to be a very, very big number as well. And it's linear, meaning that this vector is linear, meaning that like if this is when delta x is equal to 2, then if I scale up delta x by a large amount, it still stays on the same line, right? So this is like when delta x is equal to 100. So at the end of the day, since cross product really only cares about orientation, setting delta x to some specific value isn't going to change our answer, right? In fact, this is going to make our math a lot simpler. And same goes with the delta y. It's just a scaling factor for our vector, but the scaling factor doesn't change our final value, right? Because the cross product only cares about orientation, and so we can actually do something pretty nice. We can say delta x is equal to 1, and delta y, let's just set that equal to 1. Let's make the math simpler. So after I get my new vectors, remember the cross product is going to be the determinant of this matrix. So we're going to have ijk, I hat, j cat, k hat. And this is going to be 1, 0, f sub x. And then this is going to be 0, 1, f sub y. And the determinant of this is going to give us our normal vector. So I have spared you the algebra of calculating the determinant of this matrix. And remember that at the end of the day, well, this plane is going to be passing through our point, right? x0, y0, z0. Just like in this diagram right over here, right? This is a tangent point to a plane, this is a tangent plane to a point. And this point A, a lot of times we're often going to be given that information already. So let's say we're just going to call this x0, y0, z0. And so the equation of our plane is just going to be the dot product of this point and another arbitrary point on the plane. And if you remember the proof of that, hats off to you. So this is going to be the point normal of our plane equation. So this is going to be y minus y0 plus z, plus 1 times z minus z0. And we're going to set that equal to 0. All right. Now, if I move z0, if I move this portion, and if I move this portion onto the other side, I'm going to get that z is equal to z0 plus f sub x minus x0 plus f sub y times y minus y0. And that's going to be the equation of our tangent plane. All right. And just looking at this formula, that just automatically leads us to the second interpretation. Notice how this formula right over here, that's just the combination of these two formulas, right? So imagine if this was like a linear approximation in both the x direction and the y direction. And that makes sense. Intuitively, that makes sense. Because if you think about what the tangent plane represents, well, it represents linear approximation in both the x direction and the y direction combined, right? If you zoom in onto a surface closely enough, God, I don't know what happened there. But if you zoom in onto a surface closely enough, it's going to look like a straight line in both the x direction and in the y direction. And so if we want to put this together to form a tangent plane, it would be very similar to the local linearity problem that we visited before. That is how you calculate the tangent plane.